Where we left off last time, and today we're going to be talking about everybody on randomized algorithms. So just a quick review. So last time we discussed network topologies, how that relates to MPI, and then we went through some of the basic MPI API, and we considered matrix multiplication as an example of an algorithm that gets mapped effectively and efficiently onto the underlying topology. We're going to sort of continue questions before I move on. Actually, maybe let's do a couple of logistical issues. So for this assignment, there are three questions, or three main questions. Two of them are primarily programming with some sub-bullets where I want you to. So I want you to not treat this only as a programming assignment. Give equal weight to what you code up, the kind of experiments that you run with those, and what you write in your report. The TA will make sure that your numbers match and your code is written and it does what it claims to do. I'm going to grade the reports. So I expect one report from each group. I told you groups of 2. You can log on to Canvas. I'm trying this on for the first time. I don't know if you guys got an email. I set up groups. So you should go and self-enroll in groups. So I've created 25 dummy groups. I think it should be there. So you should go and add yourself to one. So if you and your teammate are there, so just add yourself to one particular group. Pick whatever number you want. That way, I only need to grade one report, and I can automatically assign the grade to both of you. Choose your teammates wisely. Make sure you both contribute. This has to be at the level of making sure that both of you use Git, work distributed. This is sort of, we're looking at parallel and distributed algorithms. I want you all to work in a distributed fashion as well. So work independently, check in your code. I'm going to ask the TA to make sure that on the GitHub, so for your final submission, that there are sufficient and well spaced out commits from all team members. So make sure that happens, and submit the report. What else do I want to talk about? Any concerns on this? So make sure all of you run the experiments as well. So it's not just about taking the algorithms. For most part, the algorithms are things that we have covered in class. I want this to be somewhat open-ended. So even though you'll find that especially problem number 1 and 2 are very specifically defined, I want you all to be open as you come across issues. If you want to explore further, I've asked for the most simplest algorithms to be implemented, but they are not actually ideal. So if you guys are interested, I'll probably add some additional notes following the assignment. You can keep this copy as the official assignment. I'll add extra points on possible extensions or possible variations to consider. Hopefully some of those will be obvious to you as you run the experiments. So go through this. If you have any questions, email me, email the TA. The second thing I want to say is that there are some people in this class who do not interact. You all probably know who you are. Some of you interact, some of you don't. Please try to interact. If you have concerns about this assignment or the course in general, email me or stop by during my office hours. I have office hours tomorrow as well. So make sure you're comfortable with this. This is going to be using MPI and C++. You will have to spend some time familiarizing yourself with MPI. Hopefully the assignments themselves are fairly simple, that you spend half the time getting comfortable with MPI and the rest of the time implementing them. Okay? Assignment, the problem number 3 on its own is a pen and paper assignment. You do not need to program anything for that. There is a programming task as extra credit for those who are interested. So if you didn't do well enough in the first assignment, or you're just done with everything else and you're happy with what you've done, you can take a shot at it. I want you all to think about it. It's a fairly simple problem, but it's a very interesting problem. It's something that if you Google, you probably will find the answer to. Even if you're planning to do that, spend at least a couple of days thinking about the problem. It'll do you a lot of good. Okay? And focus on the report. Make sure, yes?
I'm just kind of concerned. I feel like it's not enough time to do really the assignment the way you want to, especially to get everything out of it. I know in the syllabus you said 3 weeks, and I'm doing.
Yes. Yes, it might be a little bit tight but it's tight for everybody.
Right.
Why did you start? Next Monday, which would be 1 week from now and 1 week left, let me get a feel for everybody. I will extend it. But I don't want you to start off with the assumption that you're going to get 3 weeks and work in the last 2 weeks. Or the last week. So why don't you start, get a feel for it, come to me with issues, tell me where you are having trouble, and then I'll extend it if everybody is there. Because it's still an even playing ground for all of you. So try to push yourself as much as. I want to cover a lot of it. I want to cover additional topics and additional issues in the subsequent assignments. I don't want to limit that. So don't worry too much about your grade right now. Everybody has the same problem that you're going to have. So do your best, get to where it is. It's 2 problems. Strictly speaking, it's not going to take you that long once you get past the initial understanding of how to write the code. Yes?
I just don't know why, because I was reading one of the paper you posted, the one they did the analysis, and they made a statement. They said the sample sort was the hardest one to implement. I don't know why.
So yes, it is. But you are not implementing the hardest version. What you are implementing. So it is hard if you consider all the scenarios. If you consider very large numbers. There are a lot of cases that need to be handled. You are doing it for a very specific input set and 2 specific distributions. You're not. So implement the default version first. So this is an assignment level implementation. If you had to implement sample sort correctly to handle every single type of input, every single scenario of N and P, you're going to have issues. We are only going up to 16 nodes. So you're still operating in a specific way. I'm hoping that some of these issues come forth. I want you to understand it. You can continue and implement a much better version during the rest of the semester. You will, so if for all of those who are interested, you can focus on this. I will ask you to implement sample sort, or it'll be open, some sort of a sort algorithm on Hadoop as well. So I want you to compare both versions, what is easy, what is not, and get a feel for it. So many of these implemented perfectly can be very hard. The second algorithm, and this is sort of the other thing that you should take home from this, is that randomized algorithms are harder to analyze but are very easy to implement. So you'll see this, that it looks like a hard problem. And to some extent, sample sort is randomized as well. It's a kind of a divide and conquer rule algorithm that relies on sampling, which is in itself randomized. It's not deterministic. So if you run it 2 or 3 times, you're probably going to get different run times. It's not going to be exactly the same. Even the data movement is going to be different. So these algorithms end up being easier to implement in parallel because it's random, there is no direct connection between your data. So these are going to be easy to implement. And if you have issues, come and talk to me.
Okay. Just one more quick question. Is there any library to visualize the graph? Anything we can use?
Why do you want to visualize the graph?
I think it's just so much easier. We can just kind of see what the output looks like.
For which one? For the graph coloring?
Yep.
I'll try and find something, and you should be able to. I'll write something so that you can visualize it. But it shouldn't matter, but if you want, fine. So there's a very popular package called GraphViz, and you can just write this out in that format and visualize it if you want. So if you have, how many of you have looked at the assignment posting? Okay, so if you see, I've given a set of graphs, and those graphs are very small. They're not massive graphs yet. That's the other reason. Scaling this to really large graphs is in some sense much more challenging. So it's a small set of graphs. You can run all of those graph coloring algorithms sequentially on your laptop if you want. They're not that large. So You might even be able to find some packet which colors it and visualizes it automatically. But I'll set up something so that you can visualize it if you're that interested. Yes?
So to get started with the assignment, is there any study material that we can start? I mean, I saw the MPI reference, but I think it's too wide the scope.
What do you want?
To just start with how to code and everything.
Did you look at the MPI examples?
The reference book that you put up?
No, the TA said she has uploaded some assignments.
Just two samples. That should be enough to get us started? Or?
I should think so. If you want, I will upload a skeleton code for both algorithms. Is that fine? Okay, I'll upload skeleton. So maybe by the end of today, start working on your own. I'll upload a very rough skeleton. For those of you who are more ambitious, don't treat it. It's going to be the most simplest version that I'm going to sketch out, okay, with which steps are missing, okay? And most important in all of these cases, look beyond just programming it. Make sure you spend enough time running the experiment, looking at the results, trying to see what the experiments tell you. So this is a grad course. I want you to think beyond just that, he asked me this, I answered this. So think about giving reasons for it, justifying what it is. So if I've asked you a question like, you know, can this be done in order n? Don't say yes and no, say something beyond that. So think about that. This is especially important, so focus on your report, make sure the report is well written. You are going to get, you know, your credits depending on how well you write it and how well you present the results and what all you've thought of. So if you thought of issues, if issues showed up, make sure you talk about it. It's especially important for problem number 3, which, like I said, is you can implement it if you want to, and hopefully if you get it right, it's easy to implement. So let's consider I/O. I will actually set this up for you, so you can ignore some of this if you want. I'll set up a very simple, actually no, this you should do, this is part of it. I'll set up a simple scenario for both for the sort and for the graph carving, at least a sketch of the code that you should think about. I/O is important, and in an idealized sense, because we're doing things in parallel, I/O has to be done in parallel as well. Reading and writing files from disk is the slowest part. So if you think of the hierarchy that you have accessing data, which is sitting in your registers versus your cache versus your main memory, the I/O is the slowest, and it's slowest by several orders of magnitude. So it's important, and we are limited by the technologies that are available out there. So parallelizing this is an obvious way, and reading and writing, because they can be done in almost an embarrassingly parallel way, is a very easy way to increase the bandwidth. It's hard to coordinate and optimize if you're working directly at the file system level or at a POSIX I/O level. So several frameworks give you tools which are higher level functions to allow you to do this efficiently. And think of why it's there, because fundamentally, when you think of parallelism, you don't want to add an extra layer of complication in terms of what is my underlying file system like, how many disks does it have, how do I consider parallelism at the file system level. So that's why we prefer to have this abstraction where I don't have to directly deal with it. For those of you who are going to eventually implement something very high performance and you're really trying to squeeze out the last bit of I/O bandwidth, you might have to do this. And you're going to notice this difference, that it's also somewhat asymmetric. We don't deal with asymmetry as much when we consider doing computations and solving algorithms in RAM, but in I/O there is a huge difference between the kind of bandwidth you can get while you're reading files versus the kind of bandwidth you can get while writing files. So high-level APIs for managing parallel I/O make it much easier for you. So the most trivial thing that you can do is, what a lot of people actually end up doing, is to use sequential I/O in parallel programs, which means that if you think this is your distributed file system, this is a massive file that we have, you're going to get the root node or one particular process to read or write the file, and then do a gather or a scatter to exchange that information with everybody else. In some cases, this might be the best way to do it. If the file is really small, if you're considering really small and it doesn't make sense to parallelize the actual reading or writing of files, you might want to do this. And you should consider this as an option, especially when you consider the I/O strategy for reading your graphs. So if you have some very complicated data structures and they are small, this might still be the best strategy. If you have relative data which is not very tightly coupled and it's very clear how you want to partition it across your processors, then you want to do the opposite strategy, which would be to really do it in parallel, which means that every process reads a different part of the file. Now you can think of doing this sort of the poor man's way, which is that you can take this file, you can have in your script, when you're submitting jobs, you have a script. You can take this and you can break this into pieces and then say that each process is going to load their own chunk. So the problem with this is that there is a lot of redundant I/O. You're doing disk operations when you split this file and write new split files. Also, when you run your experiments, and in reality when you run your actual problems, you want to consider the case that the way you would split the file is going to be depending on the level of parallelism you expose. So it's not really a very efficient system unless you're always running the same scale of problems. So the better thing to do is to have a single file, and you'll see that this is an approach which is quite common in the MPI HPC domain versus Hadoop, where it's fundamentally distributed and it is actually stored in chunks and maybe even in a more aggressive fashion than the level of parallelism that you expose. And then the MPI I/O part, or the API itself, allows you to read the same single file in parallel by different processes. Okay. What are your thoughts on the two approaches? Which one do you think is better? Or somebody said this one?
I mean, so it depends on how your file system is set up and how you connect these. So,
what are the advantages of trying to have a single file as opposed to split files? No, you need to think beyond, because at a implementation level it doesn't matter. So the main advantage of going for something like this is interoperability. So let's say you do some processing, and that processing, so he talked about visualizing graphs, right? If following an analysis you want to say visualize results, you don't want to then deal with additional things. So if you're moving things between systems, if all your analysis, all your accesses are guaranteed to be distributed and on maybe the same system, then that's fine. The moment you bring in interoperability, then in most cases, having a single file and letting the file system itself deal with accessing it in parallel would make sense. Okay? So it's not, eventually you might not have, this is sort of some might end up being beyond your control, but it's sort of good to know. So when you consider I/O within MPI from an API perspective, it's not really that different from sending or receiving messages. So you can think of writing as sending a message and reading as receiving a message. So the API is mostly going to be there. You're just going to, instead of using a process ID, you're just going to use a file handling. And it's good because you can think of it the same way as you would think about communication. It's just something with a much higher latency and lower bandwidth. So you need to consider that, but other than that, you can analyze your I/O patterns similarly. And the I/O features of MPI were not there in the original MPI standard, and they were introduced in MPI 2. And since then, the early implementations were not very efficient, but what you will see nowadays on most modern systems is that this is very effectively implemented, and in most cases is tailored for the underlying distributed file system. So like I said, you need to figure out, so the level of parallelism that you need to use for reading and writing is going to depend on the distributed file system, the number of disks they have, and the number of hosts which are actually accessing at any given time. You can go ahead and opt for a low-level API and say that I have 500 disks there, so my striping and the level of parallelism that I'm going to expose is 500. but you don't have to deal with it if the system is well set up. And then basically the system administrators for your clusters have already configured this, and you don't have to worry about it. And again, the parallelism is that you can go via MPI where each process independently participates in reading and writing files. The standard functions that you have to deal with are file open and file close to open and close a file. This is going to be a single file thing. Again, everybody does this in parallel, and everybody gets an independent file handle. There are a few different variations on how to position where you're going to read and write. Now, if you think about how we talked about distributing work in memory, we were using the ranks to figure out which portions of the number. So if you had a large array, we were saying that the first process gets 0 to n over p, and the next one gets n over p to 2n over p. You will use the same logic when you're reading files. So it's no different, which means that we need to seek. This is very similar to your standard C API. So you can use individual file pointers, which is that you would seek your file pointer to a given location, which is now going to depend on the rank or the ID of the process. You can combine this with a read operation together in a single command, which is read at, or you can use shared file pointers to read across a bunch of different machines together. In addition, and this is something that you should experiment in the cases where you are dealing with I/O, there are collective I/O operations, and this is the same as the collectives that we had. So you have MPI file read at optional all and write all. This is different from the functions out here, which are standard read, because if you know that all your processors within a communicator are involved in I/O, MPI has the option of doing additional optimizations to make it more efficient. So if, for example, the level of parallelism or the number of processes that are writing or reading at the same time is less than the critical threshold for the number, say the number of disks in the file systems, at which point the performance is going to change, then it probably doesn't make a difference. But if you are, say, involved in a parallel I/O, which is at a much larger scale than the underlying file system supports, then MPI has an option to optimize that. So in most cases, these are probably going to be the most efficient ways for you to read and write. But I would expect you to experiment with this, yes?
But even with this collective I/O, wouldn't you need to know exactly this process needs to write at this offset?
Yes, you will. You will. So the only difference is that are you independently treating them where each process writes it, or do they write? So this is going to be blocking, that is going to be non-blocking. That's the difference from your perspective when you're thinking at an algorithmic level. It is quite possible that the net performance is not that different. But this, when you're planning your algorithm, you should think that this is going to be a blocking call, because everybody is going to start writing and stop writing at the same time.
So it's more like either we do the mutual exclusion by ourselves, or we let the MPI handle the mutual exclusion.
What do you mean by mutual exclusion?
Make sure no one writes to this file, like using indexes or something.
You don't have to do any of that. That's what MPI does for you. So what you're going to do, so you have to handle the case that you don't want one process to overwrite at a location where somebody else has written.
Okay, right.
That MPI is not going to guarantee that.
Yeah.
But beyond that, the fact that you have multiple processes writing to the same file is going to be guaranteed by MPI. And you don't have to go to the lower level of acquiring locks and dealing with that. But it's not foolproof in the sense that if you make a mistake, it's not going to prevent you from making it. So you have to be careful on that account. Okay? Keep in mind that this is I/O, and there are too many factors out here. So you really don't know the order in which the files are going to be written or the data is going to be written out to the file. So if for some reason you have concerns along those lines, then you have to go, you probably are better off going for the first option, which is to gather all the data together and then write out from a single process. So consider that as an option always. Yes?
Can you explain more about non-blocking I/O?
So the non-blocking I/O here is, so it's, the I/O itself is always blocking, but when you consider, well, you can have non-blocking, but fundamentally in these cases it's better for you to think of a specific write as a blocking call, right? You can implement this differently, so don't take it that IO is always blocking. But when you have parallelism involved out here, I might be able to write out my file much faster or read my file much faster than another process. If you consider these ones which are collective, you're going to effectively be blocking everybody else till the slowest process has finished reading or writing, which can have implications if you're doing something at the end of it. It might not matter if you're, let's say, writing a file and that's the last thing you do before you exit. Then maybe using a blocking call doesn't really involve much. But if you're starting work, let's say you're reading a file at the beginning, then you have to weigh the consideration of opting for a collective I/O versus independently reading, because that is still asynchronous. This might be more efficient in many cases, but it really depends on what follows after you get the data or you perform specific I/O. So that's what they're not as different as some of the other commands that we have talked about, but it's a very subtle difference that you should be aware of. Is it clear? So now let's get to randomized algorithms, the more interesting part. So I mentioned this earlier, that there are two main strategies for parallelization. There are other strategies, but it's good to at least limit us to these two strategies. The first one we talked about was divide and conquer. The other is randomization. There are subclasses of algorithms within randomization as well, but the key idea is that you ensure that you use random variables to help processes make decisions, which in most cases with a high probability will basically be a good global decision. So I already mentioned this once, but we did actually cover some random algorithms as well. We covered quicksort and sample sort. Is it clear why these two are types of random algorithms as opposed to being deterministic? If it's not, let's consider quicksort first. Why is quicksort randomized here? Yes. Might be. In most cases, we are using either it's random or you're using a heuristic. In an idealized sense, we are using a random choice. What about sample sort? What is random then? The samples. You can be loud about it. This is not a very difficult question. So, any question? So, we're going to look a little bit deeper into this as to why is that. So, okay, very simple. The most common places that you're going to see randomization show up in parallel algorithms. The first is sampling, which is that because there's so much data and we don't want to read everything, or there is a strong dependence between data, what you can do is that you can sample your data, you can get representative samples from the data and compute or analyze that based on whatever you want to do and use that as your answer. And this is actually very, very common. The other situation which we're actually going to talk about today is symmetry breaking. So in large problems, you would encounter the situation where, and this is both at the level of the largest clusters, but you can even think in terms of multi-core machines, which is that multiple processing units need access to one particular resource, and you want to enforce an order in which they're going to go so that you can break the symmetry. Because if you think of a multi-core machine, all cores ideally should be there. You don't want to have a bias in saying that I'm always going to go 1, 2, 3, 4, 5, 6, 7, 8. You want them to be equally likely. But then there is an issue of all of them requesting the same resource, or all of them requesting to be scheduled at the same time. You have to break this symmetry. And randomization is a very, very effective way of breaking the symmetry, because you're making sure that the expected scheduling of any of those or assigning any of the resources is equal, but at the same time you can define at that instant an order in which these resources should be allocated. Okay? The final thing, and this is also something which you will use very, very frequently, is load balancing. When you're designing sequential algorithms, you don't normally need to worry about load balancing, which is that who gets how much work or who gets what work. So I think some of you had this issue of also how we take the work and divide it up between processes. And again, randomization is one way of dealing with this. So let's say we're talking about the graph coloring problem. You have a graph on disk, and we want to figure out how to divide this across. There is no clear way. It's a very hard problem. And in some sense, it's as hard as the problem that we're trying to solve. So we don't want to explicitly go and figure out the best way to take our data and partition it or divide it up between our processing units. So because of that reason, randomization ends up being almost, or random allocation of data to different processes ends up being the only strategy which is sort of viable. So let's now consider sort of the first example. And before I get to what this is, you can read the problem if you want. I want you to think about the load balancing issues we had with both quicksort and sample sort. Okay? I don't expect you to implement this for sample sort, but if you guys want to, you can. But let's consider quicksort first. What did we need in a parallelization? So in an ideally randomized version, you would just go ahead and choose a random pivot and you would go. But that's going to partition your problem space in an asymmetric fashion, which means that both the convergence, the number of steps it's going to take, as well as how effectively you can divide up the work between your processes are going to be very difficult problems, and you're going to mess up with your performance. So I mentioned this briefly. You can think about it that one way to do this effectively, if you wanted to parallelize quicksort, would be to take it and choose the median. So if we have a pivot which is very close to our median, then that's a good algorithm for us to use, or a good pivot for us to use for quicksort. Okay? You can extend this. So if you think of what we're talking about here, that's the parallel k-select. And when we talk about k-selects, look at specifically, so if we say that for a given an array of size n, choosing the one select would be choosing the minimum, doing the n select would be choosing the maximum, and choosing the n over 2 or n plus 1 over 2, depending on whether it's even or odd, is going to choose the median. So we want an algorithm which, given a distributed array, will give us the kth largest. Basically, it's going to give us an element whose rank is k, if you remember the definition of ranking in an array. Okay? So how do you think you would use, if let's say you had a black box function like this, how would you use this for sample sort? No ideas? No, you don't need to do that, because you would basically call this instead. That you would, if you consider sample sort, you can perform p-1 simultaneous k-selects, which are going to be spaced somewhat like this. That I want the n over p, 2n over p, and so on selections. Okay? So this avoids a bunch of problems that we had earlier, which is that you're individually selecting and you're getting p-squared samples. So in some sense, we have avoided, if we can do this effectively, we've avoided the dependence on p-squared. You're not going to face this in your implementation because p is going to be small. But consider when p is sufficiently large, you want to avoid something where you're getting p-squared guys on a single process. Right? So this would be one way of doing it. You also avoided having to sort these, because I'm specifically requesting for this. And I'm going to talk about doing a single selection, that is not a simultaneous selection of multiple, but you can easily see how it goes about doing that. Is this clear? Do you understand the problem and why it's relevant to the algorithms we have covered earlier? So this is the basic algorithm, and it's a very simple version of a randomized algorithm. The general structure is not that different from what we have done. And like I said earlier, that most randomized algorithms end up being very simple to implement. So you start off by choosing a splitter randomly. This is random, okay? So this is not going to be an order 1, this is going to be a log p kind of. It's basically, the fundamental idea is similar to doing a binary search in some sense. But because we are not searching something explicitly, so what is the precondition for being able to do a binary search? So we want to use this to sort, so our array is not sorted. There are no assumptions on it being sorted. So we want to still do something along the same lines, and that's what this does. I'm going to say that we're choosing 2 splitters, but fundamentally you can choose, let's say, k splitters or some p splitter, some m splitters. It really doesn't matter. And for those of you who have a reasonable math statistics background, you can work out what would be the best strategy, especially when you consider, yeah, actually I talk about this, so I'll come back in a minute. So let's consider, I'm taking 2 splitters. You can do this with a single splitter as well, but let's say 2 splitters for now, okay? You're going to estimate the ranks of these splitters k1 and k2, okay? And partition, and basically not really explicitly partition, but that fundamentally partitions it into 3 sets. How are you going to rank these splitters? It's actually not that hard in order n, because you would basically go to each process and you will just count how many elements are less than 1 or greater than 1. Okay, so you're basically keeping those counters. So you take your splitters, you figure out locally on every given process how many elements are less than or greater than any given thing. You do a global reduction to get the global ranking. So you're summing up how many elements were less than k1, how many were greater than k1 but less than k2, and so on. Once we have figured this out, that's how you can basically partition it into 3 sets. You're not really moving any data. You're just keeping that all local. All you're doing is recursing on which of these to go through. Is it clear?
How did you get this reduction to in global ranking? How did you get that?
So on each process, let's consider just a single. Just consider a single splitter. I can take my elements. I'm doing a local count, and I'm basically pinning these, right? I'm saying that these are the elements which are less than k1. These are the elements that are greater than k1. Okay. I need to figure out what my global rank of k1 is. Correct. So I take the counts of those that are less than this, and I do a reduction. That tells me what the global rank of K1 is.
So in this case, you'll be splitting into multiple processes, and you'll be getting local rank from each.
Doing a reduction, you sum them up, yes. So that gives you the ranks of each of them.
But why did you say estimate ranks?
So
you know the actual rank, right? But why are you calling it estimate?
Not get a rank from splitter.
no. So it is the actual rank. It is the actual.
Rank.
It is the actual rank. You can make this further randomized, but yeah, in this case, let's ignore it. It's not an estimate. It is exactly compute the. So you are computing the exact ranks for these splitters. What you now have, that's why I chose the example with 2 splitters, is that you can actually have subsections on each process of which set to recurse on. Keep in mind that you might have different sets on different processes as these are partitioned. And that's why it's sort of a binary search, because you have reduced your search space on each machine. Okay? And then you would basically recurse only on the subset in which k is. Depending on what the rank, the specific k that you had to select, you would go ahead and divide. Now you can think of having 5 splitters or 10 splitters or p splitters for sample sort. Okay? Recursion is on a strictly smaller set. You're always reducing the number of elements that you're recursing on. And that's why it will terminate, and that's why the complexity is within bound as well. Okay? The right choice of the splitters is going to help you quite a bit in terms of making sure that the factor by which your problem size reduces is sufficient.
So, quick question.
Yes.
When you're recursing on the smaller sets, you still have to do, you'll have to talk to other processes to know the rank of the middle stuff, right? Let's
No.
say.
It's the same process repeated. You go back and you redo your ranks.
Oh, okay. Makes sense.
And so it's actually a little bit, okay, I skipped some details, I'm sorry. It should have been on the slide. But fundamentally what you do is that when you recurse, you're going to call kSelect on say R1, R2, but you're going to update the rank that you're going to call recursively on. So you won't call it with rank K, you won't do a kSelect on it. You will do K minus rank of R1 because that's the relative term, that's the element you want.
But from all the processes, I would be, let's say if all the processes have the same elements, I would, in all the processes, I would be ignoring 0 to R1 and then R2 to N.
Yes.
Okay.
So you will ignore those, you will recurse only on these. So if it is on, so let's say the K is between 0 and R1,
Yeah.
then I recursively call kSelect with K again, because that's the rank. If I had to recurse here, I would do K minus R1. If I had to do it here, then I would do K minus R2. Is that clear? I'm sorry I didn't put it on the slides. I'll fix them before I put it on there. But basically you have to make that correction before you make the right recursive call on these. Okay? Now here is an important thing. When do you want to terminate? So you will ideally terminate when you're down to a one select, basically, and maybe in an array of 1, right? Which is that you've reduced the number of, the size of elements that you're considering till you go. But in many cases, including things like quick sort and sample sort, you might just say that I don't care, I don't need an exact K. I just want to be within 10% of K. So if I'm choosing the median, I don't care if it is exactly the median, but if it is between 40 and 50% or 40 and 60%, I'm fine. So you can actually terminate this sooner, which sort of ends up being another general property that is nice in randomized algorithm. It's where you can define and specify the level of accuracy that you want. So this algorithm works very well because in most cases, especially if you're talking of millions or billions of numbers, I'm fine getting within 1% or 10%, or not maybe 10%, but say within 1% of your error. So you know what is the range. So you're not really looking for a kSelect in the sense that give me the 1,200,000 fifth element in this array. You can say that if I'm between 900,000 and 1100,000, I'm fine. So you can actually look, you can have your implementations which are somewhat tolerant to this because you know that you're going to use it subsequently and there that level of tolerance is good enough. Right? Is it clear? Because as we recurse, we are getting closer and closer to our answer. And you don't want to spend too much work. So you need to make a choice on when the trade-off is worth it. Is it better to do 3 or 4 extra iterations just to improve the accuracy of your K selection by a few percentage points? Is it clear or no? So because it's an iterative and it's refining on the value of the solution, you have that thing. Like I said, there's a trade-off between the number of splitters at each iteration and the number of iterations to converge. So if I choose a lot of splitters, right? So instead of choosing 2 splitters, if I can go with 10 or 100 splitters at each point, right? What does it mean? How is that going to affect? I can narrow down. So you can think in an ideal distribution. Let's say that these are uniformly distributed. Then that's almost like the level of reduction. So that's the log base factor that I'm talking about. Are we splitting it into 2? Are we reducing the problem by a factor of 2? Or are we reducing it by a factor of 100? But at the same time, we're increasing the amount of work we do. So this and the amount of communication we do because you're communicating and you're doing reductions on these number of splitters. That's your communication costs there are a function of that. So depending on whether you're at a system where latency is more important in this case, or the bandwidth, you might opt for that. Whether to choose more splitters or to choose fewer splitters and let it iterate a little bit further. Okay? So that's the trade-off that you need to consider. if everything is super fast in a shared memory, like a complete idealized shared memory implementation, you would just go for a single splitter and recurse further down because you're still getting a log P reduction. Okay? Sample sort is very efficient if you do it this way because I need to choose a large number of splitters because I am actually estimating that many simultaneously, which means that I'm not wasting as much work in ranking P-1 splitters. So even for quicksort, if you were to choose only the median, you could go ahead and say that I'm going to choose P or P-1 splitters and I'm going to reduce my problems. I'm going to get something which is very accurate very quickly. But then you're doing a lot of work ranking P-1 splitters in a non-sorted array. So in sample sort, I can simultaneously do it because all of those are going to very quickly make sure that my correct range of values on each process are selected, allowing me to efficiently estimate the splitters. Do you understand this? Or think of how you would use, again, I repeat, how you would use a multi-case select to implement sample sort. Okay? What do you want to do for quicksort? I mentioned a few strategies. Think about it. Think about a very, very large array, maybe a very large machine as well. So N and P are both really huge. What do you want to do? How many samples do you want to choose? How many splitters? Why? What if P is really huge? Do you really care for that much? Go back to the range at which I'm going to be able to do this. Do you need all of them to get involved? Do you need to rank it completely? You can go more probabilistic, which means that you can even make it simpler and say that I'm only concerned about getting samples from my global distribution, which means that I don't need to get every single process to be involved as well. I'm only trying to estimate the median, right? And I'm fairly flexible with where or how accurate or how close I want it to be. So you can randomly choose from, again, this is going back to the traditional sample sort approach. You can start choosing that not all processes get involved in this reduction because you know what you're trying to rank is only the median. So if I say that I make an assumption that my data is uniformly distributed, I can actually even go sublinear in some sense because I don't need every single process to get involved in this reduction. Do you understand? Or look at the trade-off between the number of samples you want, how accurate you want it to be, and how many processes you want to get involved at each stage. So because choosing a median, so let's say that there are like 1 million data points out here. How many samples do you think you need to get a reasonable estimate for the median? Assuming it is uniformly distributed and there is no bias.
Distribution in the sense that
The way the numbers are, whatever you're trying to sort. So that is a distribution of that, right? You need to look at all of them to get a approximation to the median. To get the exact median, yes, you have to look at everybody. But you can go ahead and say that I need it for a pivot. I don't need it exactly. You're not quoting somebody the number and saying that this is the mean or this is the median, right? So what we would do is to just sample it and correspondingly take it. So for example, if you had 1 million entries and you say that I'm going to just, because it's uniformly distributed, I'm going to take 1,000 samples from this and I'm going to take the median or the mean of those. Is that a reasonable guess?
Well, I feel like it also depends on what's your threshold for error. If you're okay with big error, then I need very less sample.
No, exactly. So here you can define the error in terms of percentages, right? So let's say that I say that I want my error to be, if I make an assumption on the uniform distribution, then, and I take 1,000 samples, right? Then I'm less than 1% error off, so that's fine, right? All of this boils down to you making an assumption on what the distribution is. None of this holds true. You can come up with other estimates if you have some prior knowledge about your underlying distribution.
But you're also assuming the randomization is...
Yes, you are. You're making all of those assumptions. And to some extent, that's why this is good, because this gives me an explicit number. Because I know that I need rank 500 and I'm 480. And I'm like, okay, that's good enough for me, assuming there are 1,000 elements, right? That is good enough. So you can explicitly define it as opposed to having to make an approximation. So this would basically lead to an early termination criteria. You can say that as long as I find a splitter whose rank is, say, between 450 and 550, stop. Done, right? So you need to consider these aspects because you are going to get data sets. When you sort, the data sets will be there by tonight. One of the data sets, which is what you should look at most, is a uniform distribution. The other one is not going to be uniform. And I want you to look at, if you want to fix it, you can go ahead and fix it, but you don't need to. But at least run it and see whether your default algorithms performs well enough on that or not. So consider that. Okay, let's actually switch to graph algorithms. This is a very beautiful algorithm, but before we get to graph coloring, let's talk about what a graph is, okay? So, like I mentioned, we'll cover this in detail later, but fundamentally, like what we talked about the networks earlier, it's a given set of vertices which are connected together by edges. So, if you define a set of vertices and a connection between them, that's your graph. Keep in mind that you might have weights or some sort of a factor associated with both the vertices as well as the edges. Okay? For a lot of the algorithms that we are going to look at, it's important to realize a relationship between graphs and matrices. So we kind of looked at matrix-matrix multiplication. You'll see that across large, say, very different fields in science and engineering, you will see matrices coming up and graphs are no different. So you can think of a matrix being represented as a graph being where it's called the adjacency graph of a matrix where an edge exists. So if you had an m by n matrix, let's say, a symmetric matrix in this case, then we're talking about an edge existing if there was an entry which is non-zero. So no edge exists if you have a zero entry in the matrix, otherwise an edge. And then, like I just mentioned, the weight of the edge itself can be the value of the Aij matrix. Is this clear? How you would go between an adjacency matrix representation of a graph and a matrix and a graph corresponding to that. Likewise, you can take a graph and go back to a matrix, which would be that it's called the adjacency matrix. You have a weight of 1 if an edge exists, right? If you have vertices I and j, and the value of Aij, the matrix, is non-zero, then, if an edge exists between these two vertices, then you have a matrix where that entry is 1. You can have some other representation. If there was an edge weight, you can set that. What is important to realize is in terms of how they relate to symmetric and asymmetric graphs, where you would have undirected and directed graphs, right? So this is how we would normally realize this. You want to think about this because you're going to implement a graph algorithm and you want to think of the way in which you're going to store this information in a distributed sense, okay? So storing an adjacency matrix for a graph is a popular way of storing this. Why do we want to partition graphs? Sorry, I jumped across here. So why do we want to color graphs? We want to color graphs because the first part of many graph algorithms, any kind of analysis, would be to partition this graph. So if you have a graph, let's say coming from your Facebook friend circle and the whole network that you have, and you want to do some analysis on this, but it's too large to fit in memory, I need to first figure out how to take this information and divide that up across my processes. And we will go through, it's an NP-hard problem, so it's very hard for you to solve. There are approximation algorithms to graph partitioning, and we will go through a few of these in detail later. But it sort of ends up being a chicken and egg problem, because in order to do some of that, you need to have a partitioning in the first place, because these graphs are so large that we can't load it efficiently. And coloring ends up being a prerequisite for this. And I just hold on a minute and I'll tell you what exactly coloring is. The other sort of problems which end up being very commonly encountered for graph algorithms, and we will go through some of these, is computing the graph Laplacian and the eigen problem, which is again in turn related to the graph partitioning problem. So for those of you who are used to eigen problems in matrices in general, the second eigenvector defines a very nice way to partition a graph. It's sort of the mathematically correct way to partition. But that said, this is a hard problem which requires graph partitioning to start with. We've talked briefly at some point about breadth first search and depth first search. We haven't considered, but we will go back to connected components, which means that if you have a graph, you want to figure out which parts of which nodes or which vertices in this graph are connected together. Think of it in an imaging sense of segmenting out two areas of the graph. A related problem is that of spanning trees, which is that what is the spanning trees and minimum spanning trees, where you have at most one edges and you don't have any loops between vertices. What is the minimal graph, which is a subset of the graph that I give, where the weights are minimized. If you have edge weights, then it's the total sum of the weights is minimum. Otherwise, it's just the number of edges that are minimum. So graph coloring sort of started off earlier from the standard coloring problem, where you had people who were making maps and you wanted to separate out different countries and you wanted adjacent countries to not have the same color. These end up being planar graphs in general, and there are theoretical proofs for the number of colors it requires to color up a map of the sort. Can you see why this could be represented as a map, as a graph? How would you represent this as a graph, this particular map? If they share a border, then you have an edge between them. So I want to color them up. Okay. This is a trivial problem in some sense, because, like I said, these are planar graphs, and you can color it up with 4 colors. If you start having weird connections, basically, if any given vertex is connected, it basically the number of other neighbors that it is connected to has a direct edge to, that's going to limit the number of colors that you need. And you can think about why this is hard to do in parallel, because the straightforward way of doing, actually wait, let me actually take a small detour here. Let's consider the sequential greedy algorithm. Okay, like I said, this is an NP-hard problem, so we are going to go for approximation algorithms. In this case, the approximation is in the sense that we might not end up with the least amount of colors that are required. So ideally, given a graph, there is a minimum number of colors that are required to color this up so that we can separate them out. But when you go for a greedy approach, you might have to use maybe 1 or 2 extra colors, because you are not very efficient in assigning colors when you approach it in a greedy manner. You all know what a greedy algorithm is, right? I'm maximizing it at that instance for whatever is maximizing my gain. So you're taking the most sort of the trivial approach to it. So let's consider this case where we start off with n vertices total in our graph, and we just say that let's choose an arbitrary permutation. You can think of this as being a fixed permutation as well if you don't want to think of this as a randomized algorithm. Okay? So we go through our vertices in a specific order, which is basically pick one vertex from the permutation that you had. You look at all your neighbors. When you look at all your neighbors, pick the smallest color which has not been picked up by any of your neighbors. Color yourself and move on. So depending on whatever permutation you chose, you're going to get a set of coloring. Okay? Is this clear? Why is this a problem if you want to parallelize this?
You have to compare to all your neighbors, and your neighbors can be in any other process.
Yes, which means that you are enforcing some deadlocks because you don't know who's going to be doing it, right? It's still limited somewhat by the order. This works because there is a specific order in which each process or each vertex picks their own color. At any given time, only one is. So if you think of a situation where you have two vertices out here sharing a set of neighbors, right? And they both might pick up the same color. So the bounds are fairly straightforward here. What are the bounds? You're going to be limited by the number of neighbors, so some estimate of the degree, the maximum degree of a given vertex, and the number of nodes.
Yeah.
And you can also think in terms of D being equal to C, because in an idealized sense, that's the minimum. In some cases, you might not be able to color, but that's the bare minimum number of colors that I would require. D plus 1. If I have a vertex, I have D as my maximum number of connections that any given vertex can have. So I've already assigned D color, so I have to pick D plus 1. So that's the theoretical bound no matter what. In some cases, you might not be able to get a coloring of that sort, but that's beyond the scope of this class. A related problem is that of an independent set or a maximum independent set. An independent set is defined as a subset, right? As a set basically where no two vertices share a common edge. So what is shown here in red are actually in this case maximum independent sets, but they're all independent sets as well. So you can see that everybody out here doesn't share an edge, and all the red vertices do not share an edge, right? Why is this related to the coloring problem?
If you want to highlight some states like the graph.
No. These guys can color themselves independently. They do not share it. So they can all color themselves independently, or they can all color themselves the same color.
Yes.
Okay? So understand the distinction between an independent set, where the definition is written on the top, and a maximum independent set is an independent set such that no other independent set is a superset. Okay, so that's the largest set out there. And these are actually examples of maximum independent sets, because you cannot have an independent set for which any of these is a subset.
No, it's not number of words is being for.
It's not number, it's just that it's a set. It's a set. But I can't add one more edge out here so that it doesn't violate the maximum independent set condition. That it no longer remains an independent set there. So consider the first case, because that's a little bit trickier because you only have two in the set. But if I add any one of the other guys, it no longer remains an independent set. Is it clear? You add that, he's sharing an edge with the top left. You had any of these, they're sharing with either that one or this one, and the same holds here. Right? So, yeah?
Is it like the bipartition of graph?
To some extent, yes, you could use this. So this is just a definition of a set, so that it's kind of like creating a matching out here. Although there are some restrictions because there is no requirement on all of them being connected. So, but other than that, it's basically a subset so that it doesn't have any edges within each other. That's all. So now, ideally, if you think from a coloring perspective, you want to pick these guys, right? Because I can start off by these four being. So in this case, it's very simple. How many colors do we need for a graph like this? Two, right? The red ones and white. This is a perfect one because nobody's sharing edges. So this is perfect if you can get this. So now, if you think of having a maximum independent set, so if we can figure out either independent sets or maximum independent sets, we can go ahead and color them in parallel, right? Choose an independent set, then it's embarrassingly parallel. Everybody color yourself, whatever you want. and then move on to whoever is left. And so this is, so this is basically what I just said, that any independent set can be colored in parallel. So you start off with vertices, and you create a copy of that or keep a count of who has been assigned a color, while non-colored vertices remain. Choose an independent set from this set of vertices which have not been colored, color all of them simultaneously, update which ones are not colored, and move on. Right? This is clear? You need to think about how this relates. Now keep in mind that coloring ends up being a very often used algorithm when you are developing parallel algorithms. Because as you can see, once you can think of it as the maximum independent set argument, that you use this to color once, but then once I'm colored, I can define an order in which I'm going to go through all my data effectively. Red goes first, then blue, and then green, and I know that all the red are independent of each other. So you've taken something which is a coupled problem and you've kind of broken up into somewhat decoupled problems, right? So the choice of how you go about coloring is important. And don't give too much weight to the nomenclature, just historic reasons that they have this kind of names. The first is called optimal coloring. And optimal coloring comes from the fact of the optimal color or the chromaticity of a given graph, which is the least number of colors that is required to color it. So if you look at the set of graphs which are given for assignment 2, you will see that some of those graphs actually have the optimal coloring given there. In general, when we do this in parallel, it means that you color using the least numbered color. So treat colors here as labels, right? So let's say that we are minimizing some factor. So that you want to say that 0 is cheaper than 1 is cheaper than 2 and so on. That means that if I can color somebody 0, I want to color them 0. The other option is to go for what is known as a balanced coloring, which is that I'm going to use these to parallelize some function. And I want to make sure that they're all used equally. So then, instead of choosing the smallest available color, you're going to use all colors equally, or which means that if I have a choice of coloring somebody, I'm going to use the least used available color. Okay? Trying to sort of balance out how they're there. Implementation-wise, it's just a matter of which color you choose to assign. So I didn't talk about this, but you can think about adding these options to your implementation. An independent set in parallel. And this is where the randomization comes in. It's going to seem extremely trivial, but it took a long time for people to figure out how to do this. So you basically just assign a random number to every vertex in parallel, right? So I will have a separate topic, a separate lecture someday on how to choose parallel random numbers, because most of you who have worked with, do you know how random numbers are generated on, if you call rand or any of your random number generators, do you know how it works? They are pseudo-random number generators, and they're sequential. So they are actually using your current one, they generate the next one. So that's why if you give it the same seed, it's always going to give you the same number. So doing this in parallel is a bit of a challenge, okay? You can come up with clever hacks to generate these numbers in parallel. I can give you, I'll post a separate note. I'll send an announcement on this, but generally something like using the rank to seed on every single processor is a bad approximation, but it'll do for now. There are better ways to generate parallel random numbers, and maybe the next lecture I'll cover that. Okay? But let's assume that we have assigned a parallel random number to every single vertex. Then all I need to do to choose an independent set is to choose vertices which are a local maximum, or a minimum for that matter. Because it's between me and my neighbors. I have broken the symmetry. You needed some factor to figure out. So Is it clear or no? So let's look at the example. So this is my graph. Now you know what the numbers are. You randomly assigned numbers to every single vertex. Yes?
Should they be unique?
It doesn't matter.
Each random?
No. So probabilistically they will be. If you have a good random number generator, they will be. And in most cases what they do is that you want a randomized algorithm as opposed to choosing a specific order so that you don't have a bias. But at least let's say that these two had the same random numbers. You would use usually the ranks or maybe the degree or some other metric to break that symmetry, but it's an easier thing and it's not as strong a bias. Okay? So now that I have numbers, every vertex in parallel is basically going to look at its neighbor's numbers. Okay? And it's going to figure out if he is or she is a local maxima or not. If he's a local maxima, he knows that none of his neighbors are going to be local maximas, which means that he is an independent set, or he's part of an independent set. Is it clear? Right? Why not?
I can choose, I mean, it's very unlikely that I can choose number in such a way that looking at all these.
You're generated numbers randomly, so somebody has to be a local maximum. And you have no. So the thing is that you could have situations where there is a tie. That's the only situation. So if you have a tie, that's why you have a fallback. Or let's say, for argument's sake, if you do this, then you basically roll dice again. You generate a new set of random numbers, break the symmetry, and move on. So the key idea here is that you use random numbers to break this symmetry because you don't have a specific order, I don't know, and you know that you want to isolate vertices from its neighbors. That's why you define a metric of this sort. Okay? And this is not a very old algorithm. And the next one we are going to cover, which is a little bit simpler, and that's the one that you need to implement, and is actually better as well. So in many cases, you will see that the simpler algorithms end up being better. So in this case, all of these guys and their neighbors, right? So anybody who's there. So effectively, except for 14, nobody is left. So that is my only graph. Because he's left, he gets added to the same independent set. I have colored them, but technically by Luby's algorithm, we haven't colored them yet. Once we have now all of these guys, this is an independent set because I have no more vertices left. Yes?
But if 14 is connected to some other set outside, if I have two remaining, then how would I do it?
You would do the same. You would pick the one which is maximum.
Out of those two?
Yes. It's the same. It's a recursive thing, right? So if this was a much larger graph, you would basically, you've removed this entire segment and you follow the same. You pick the maximum guy out there and you continue. But once I have gone through all of my vertices, I've picked everybody. This is a maximum independent set and you can prove it. Then they all go and assign the same color. Okay? How many iterations is it going to take Luby's algorithm to converge to color it? Not figuring out the maximum set. To color.
Only to color is big of one.
No.
Parallel.
He's going to take the number of colors because he's assigning one color to all the work. So this is, think of the graph metric. This is not a rigid number. If this particular graph requires C colors, it's going to take order C iterations because there's no doubt of what my choice of color is because all of them get assigned the same color at the same time. So it's like peeling an onion, right? You're basically saying that let me figure out the maximum independent set, color them all, remove it, go ahead and recurse, right? And I don't have to worry about figuring out because the first set is 0, the next is 1, and so on. Okay? And so we can recurse on this. These guys have been colored. Luby actually asks you to generate new random numbers for whoever is left. So we generate new random numbers. We pick another independent set. Let's say on one particular case, this is all there is. I have no empty left. that I'm just not going to participate at that level. Whereas whoever has it will participate and will label them or add it to the independent set. So there's a little bit of synchronization, mostly in terms of exchanging the weights in the beginning and communicating. Let's look at the other algorithm. It's a little bit simpler and it'll make it clear as well, because you're not doing it in such a complicated fashion. It's kind of a bit of a greedy algorithm as well. It says, so basically the thing is that why create new random numbers at every single iteration? I don't care. I have assigned random numbers and those are good enough, right? I'm going to throw some vertices out. I'm going to get rid of this, but they still will give me the local maxima. And they decide to use vertex numbers to resolve conflicts. You can use a different strategy if you want. You can generate a new number if required. But at least this way, you're not exchanging this all the time. You compute the weights, you exchange it once, and there's no more communication, correct? It does not find a maximum independent set at every time. It says that I'm only going to find an independent set. So remember I told you that Luby had sort of two iterations, right? The first was starting with an independent set, compute a maximum independent set, and then color all of that simultaneously. Instead, it only finds the independent set, the first part. Use the random number, get the maxima, you're part of an independent set. They are not all assigned the same color. The coloring strategy here is a greedy strategy. Okay? So there is a different kind of communication required out here. He colors them individually, even within this independent set, depending on what is the unused color from my neighbors. Okay? So here, because you are not coloring everybody the same, you can bring in your strategy of whether you want to use the optimal coloring or a balanced coloring. Is this clear? Let's look at the same thing. So you can sort of see the pseudocode while somebody is not colored yet. For all the vertices, do it in parallel, compute the independent set, and for all the vertices in the independent set, look at the colors of the neighbors of this particular vertex, choose the minimum color by whatever definition, remove them from the list, and you're done. Okay? So start off with this. We have random numbers. It's going to be the same random numbers throughout. We're not going to be choosing them all the time. So pick an independent set. 14 doesn't get picked, but I don't care. So remember that 14 would have ended up as blue in the original one. Choose another independent set. Look at these colors and say, oh, yellow is the next best color available because they're all adjacent to blues. So I'm going to color them yellow. Choose the next set, assign the next unused color. Okay? You're probably going to go with red or something because red is the least used color. Okay? Oh, sorry, not yet. Red. Yes, you'll go with yellow. Yeah. So, but I'm just saying that's how the algorithms are different. Is this clear? So it's basically pick an independent set which is sort of embarrassingly parallel, and then you iterate till you have colored everybody. Okay?